Yes. Cool.
Right, Dylan? What, Connor? What? Okay.
All right, so for today, this will come on in just a second here. For today, we're going to consider R of t, the position vector for today. And we know that r prime then would represent a velocity vector. R prime is tangent to the curve, points in the direction of increasing parameter. Our double prime is going to give us our acceleration, our vector acceleration. What we're interested in today is breaking up the acceleration into a component that's tangential to the, so tangent to the curve, and a component of the acceleration that is normal to the curve. So what's, if we're thinking of RT as a position vector, what's the tangential component of acceleration going to tell us? What is that going to do to our object? It's going to speed it up or slow it down in the direction of motion. So either speed it up or slow it down tangent to the curve. And the normal component of acceleration, that's going to make it turn. So we're interested in those two things. In 12.5, then we're going to relate the normal component of acceleration to the curvature of our curve, and we'll come up with a way to describe the curvature analytically. All right, so we defined our unit tangent vector. T was r prime over the magnitude of r prime. And we're going to call the velocity vector for now, we're going to call the velocity v of t. And we'll call v, scalar v, the magnitude of our velocity vector, the speed. And we know that n, our principal unit normal vector, is t prime over the magnitude of t prime. So what we want is a component of acceleration in the direction of t and another component of acceleration. I forgot to put my n here. N equals. And we want another component of acceleration in the direction of n. Well, what I'm going to do is use this expression to say that I'm going to write this as t equals v over the magnitude of v. So my velocity vector is the magnitude of v times t. And that makes sense. This is tangent to the curve, and that's the magnitude of my velocity. And the magnitude of t is 1, so this is going to give me my velocity vector. And we're going to, since we're looking at acceleration, you know the acceleration is a derivative of the velocity, we're going to differentiate. And we need to use the product rule to differentiate here because the speed can vary in time and our unit tangent vector can vary in time. So the derivative with respect to time of v of t, we'll write as a of t, acceleration, is the derivative of the speed with respect to time times t plus, then we're going to, this is the derivative of the first times the second, plus the velocity times the derivative of t with respect to t. What's the derivative of t? What's another way of writing the derivative of t with respect to t? Almost. Isn't it just t prime? So this is going to be the derivative of the speed. The unit tangent vector, the derivative of t can vary in time because we're moving along the curve. So it's going to point in a different direction as we move along the curve. T plus, I'm going to write the magnitude of v times t prime. Well, we're close to what we wanted, right? Here is a component of acceleration in the direction of the unit tangent vector, and here's a component of acceleration in something that's related to the unit normal vector. So why don't we write this, or why don't we make this, turn this into the principal unit normal vector by multiplying by a convenient form of 1. So I'm going to write magnitude of v t prime times the magnitude of t prime over the magnitude of t prime. Well, t prime over the magnitude of t prime is our principal unit normal vector. So I can rewrite this now, that our acceleration vector is the derivative of the speed with respect to time times our unit tangent vector. That's our tangential component of acceleration, just the scalar, the derivative of the scalar speed, plus magnitude of v times the magnitude of t prime times n. And there is our normal component of acceleration. Well, I combine this t prime over magnitude of t prime to give me n.
Is that T prime in there?
That is t prime in there. So we can say this is a sub t times t plus a sub n times n, where a sub t is the derivative of the speed with respect to time, and a sub n is this quantity, the magnitude of the speed times the magnitude of t prime. So there's our tangential and normal components of acceleration. Now these aren't not particularly nice. They're not terrible, but not particularly nice. We're going to do a little more work. So we've accomplished two things. Are we good with what we have so far? So this is our first step. We've broken our acceleration into a tangential and normal component. So what we've done, we have a sub t and a sub n. So we could say, okay, that's good enough. So that's one thing we have. But we also have that a sub t, the vector acceleration, is the sum of multiples of t and n. So that means that the acceleration is always in the plane defined by n and t. So our acceleration is always in the same plane as our tangential and normal vector, unit tangent vector and unit normal vector. So let's draw a picture. So we have a curve, like so. That's our curve. This is given by r of t. And at some point, I'm going to draw it at a point here, and this is not necessarily to scale, so it's not going to be necessarily beautiful and perfect. So there is our unit tangent vector. And I'll draw our unit normal vector here, like so. And my acceleration vector is going to look just something like this. So that vector is going to be my acceleration vector. Well, what I'm going to do is extend this like so, and make that a 90-degree angle. And I'm going to extend this, oops, that's not very good. Extend this vector like so, and make that a 90-degree angle. Well, this, remember that t and n are unit vectors, so that length is a dot t, and this length is a dot n. So this gives us another way of describing the tangential and normal components of acceleration. So we can see that the tangential component of acceleration, a sub t, is a dot t. So that's another way to find the tangential component of acceleration. And a sub n is a dot n. Now we saw that calculating the principal unit normal vector can be very difficult, and we usually want these quantities a sub t and a sub n represented in terms of our position, velocity, and acceleration. So we don't necessarily want to have to calculate the unit tangent vector and the principal unit normal vector to find a sub t and a sub n. We want to be able to use our curve and the derivatives, our position vector and the derivatives of that. So what we're going to do is we look at v dot a, v cross a, and a dot a to see what kinds of quantities those give us. Now, I'm not going to go through these calculations in class. They're not difficult, but they give us some information. I would highly encourage you to look at, I have a video. It's called 12.4 Derivations, where I go through the process of coming up, doing these various things to come up with other expressions for a sub t and a sub n. But the first one we can see pretty easily. What's another way of writing our unit tangent vector? In terms of our position vector, our velocity, our acceleration. Isn't this v over the magnitude of v? So we can see right away, and that we get the same thing from looking at v dot a, that a sub t is a dot v over the magnitude of v. So there is our tangential component of acceleration expressed just in terms of, we could also write this, and you'll usually see it written as v dot a, but I'm going to say r prime dot r double prime over the magnitude of r prime. So there it is. There's our tangential component of acceleration expressed in terms of our position vector and its derivatives. All right. Well, we can come up with some similar expressions for a sub n and some other quantities by going through these. So I'm just going to write our results. The first, this v dot a gets us to this same place as well. All right. So our results. We already saw that a sub t, or sorry, our acceleration with respect to time is a sub t t plus a sub n n. This gives us a way to calculate our principal unit normal vector without doing t prime over the magnitude of t prime. I can solve this for the principal unit normal vector. I get n equals the acceleration minus a sub t times t over a sub n. T is relatively easy to calculate. Our acceleration is just a second derivative of our position function, and a sub t and a sub n we're going to have easier ways to find in just a second. So this is going to, in general, is going to be an easier way to find your principal unit normal vector. We saw that our acceleration, our tangential component of acceleration, the derivative with respect to time of our speed, we can calculate our tangential component of acceleration that way. We also saw that it was a dot t, and we saw before, and we could look at v dot a, that it is also equal to v dot a over the magnitude of v. This is usually going to be one of these two, but this is usually going to be the preferred way to calculate a sub t. V dot a over the magnitude of v. A sub n. This isn't a vector, that's a scalar. A sub n is the magnitude of v times the magnitude of t prime. Sometimes that will be convenient to calculate. Often it won't. It's also a dot n. Sometimes that will be convenient to calculate if you have an easy way to calculate n, or a given n somehow. And from looking at v cross a, this is the magnitude of v cross a over the magnitude of v. This is usually going to be your preferred method for calculating your normal component of acceleration. And from looking at that last quantity we looked at, A dot A, we can see that this is also equal to the square root of the magnitude of A squared minus A sub t squared. This may be a very nice way to calculate A sub n also. So that those come from looking at those three quantities, V dot A, V cross A, and A dot A, doing some manipulation with them, some simplification, and taking advantage of the fact that a vector dotted with itself is its magnitude squared. A vector crossed with itself is 0. Some of that plays a part in coming up with these. So now we have a nice kind of compact way of calculating A sub t, A sub n, and a convenient way of calculating our principal unit normal vector without having to do all those derivatives that involve all the radicals. All right, I want to look at an example. We'll do a two-dimensional example. I have a video where I go through a three-dimensional example. I actually go through this two-dimensional example as well. But there's an additional example on a video. That's Calc 3, what is it called? 12.4 examples. All right, so let's look at a two-dimensional example working with these quantities. We're going to say that R of t is t squared I hat plus 2t j hat. And the question might say, this is not an unusual question for this section. Find t, n, a sub t, and a sub n at t equals 1. So all these quantities are related, so you end up calculating them all. So we need some derivatives. R prime of t is 2t I hat plus 2j hat. And we need the magnitude of R prime. Is the square root of 4t squared plus 4 for any time. We're looking at R prime at 1, so that's 2i hat plus 2j hat. And the magnitude of R prime at 1 is going to be square root of 8. So our unit tangent vector, R prime over the magnitude of R prime, I'm going to write it as square root of 8 is 2 square root 2, and I'm dividing by 2 square root 2. So I can write this as square root of 2 over 2 I hat plus square root of 2 over 2 j hat. Now we're going to go on to our other pieces. I'm going to calculate n at the very end because I want to calculate a sub t and a sub n first. All right, R double prime, we need our acceleration. R double prime at t. Well, this is not complicated motion, so our second derivative is pretty nice. 2i hat. A sub t is R prime at 1 dot r double prime at 1 over the magnitude of r prime at 1. That's a nice easy quantity to calculate. So we get 2i hat plus 2j hat dot 2j hat, or sorry, 2i hat over 2 square root 2, square root of 8. And this just gives me 2 times 2, 4. So 2 over square root of 2, square root of 2. So our tangential component of acceleration is square root of 2. Our normal component of acceleration is r prime at 1 cross r double prime at 1. We're going to take the magnitude of that because we don't want our normal component of acceleration to scalar quantity over the magnitude of r prime at 1. And when we take r prime at 1 cross r double prime at 1, we're going to get, just like our integral of the day, we just get a k hat component. So it's the magnitude of minus 4 k hat over the square root of 2. No, sorry, over 2 square root 2, square root of 8, which is square root 2. Magnitude of negative 4 k hat is just 4. So there's our normal component of acceleration. Now we can calculate our principal unit normal vector relatively easily. Our principal unit normal vector at 1 is the acceleration at 1 minus a sub t times t at 1 over a sub n. And we have all those quantities. 2i hat minus the square root of 2 times the square root of 2 over 2 I hat plus square root of 2 over 2 j hat over the square root of 2. And we just get I minus j over the square root of 2. And there's our tangential component. Or sorry, there's our principal unit normal vector at t equals 1. Yeah?
When we found a sub t, how did you got the numerator?
So 2i hat, we're just multiplying the I components, multiplying the j components. So this is just 2 times 2 is 4. I don't have a j component, so I just have my dot product is just 4.
Okay. That makes sense.
It seems like it's 2 over root 2, right?
4 over root 2. 4 over root 2. No, 4 over 2 root 2. So we get 2 over root 2,
Multiplied by root
which we rationalize to square root of 2.
Do we have to rationalize, or if we left it as 2 over root 2, that makes sense?
I would suggest rationalize it, something like that. I would rationalize. The other's okay. All right. So if you had a three-dimensional vector, each of these calculations would have an additional component. So not a lot more work, but a little more work.
Choose your number. Just have the square root of 2.
All right, questions? So what we're going to do next time is use this idea of tangential and normal vectors, normal component of acceleration, to come up with an expression for curvature. We'll do that on block day, and then on Friday we'll relate curvature back to some formulas that you probably learned in physics that have to do with curvature and acceleration. Yeah.
Is there any curve sketching on the quiz?
Um,
'Cause I can't do that well. Like I can visualize it, but I can't put that on
Oops.
paper.